So I want to remind you guys a little bit about what we said yesterday. You might already have this written down. Oh.
What?
On time. Now we can start. Don't worry.
Thank you.
Okay. So if we think back to what we used to do, we used to use those rectangles to help us approximate areas, and that was kind of our basis for the finding the area, the exact area under a curve. We're actually just doing this right now in AB. Your friends in AB are working on Riemann sums and all that stuff. They're actually,
that's so cute.
it is so cute. They're actually doing really well. They're doing awesome.
Really?
So, yeah, they generally are. So I'm pleased with how they're doing. But of course, when you are finding the area of a polar curve, rectangles don't make a lot of sense. That's when we're going to be using the sector to help us express this. So I drew some picture, I know, yesterday of, I don't remember. It was, I want to say it was like a cardioid or something. I'll do the same today. Just going to do this in one shot. Oh, that's pretty close. A little lopsided. It's a little lopsided, but I can go with it. So like I mentioned to you guys, what we're going to do here is we are going to essentially accumulate sectors. So this is pretty nice. I think this will be a pretty nice view. I want you to think about this. Wouldn't a sector, you could think of this as like a right sum sector, sort of?
Yeah.
And then this would be the next right sum sector. And a sector is explicitly a part of a circle. It's not a part of a cardioid or a part of a lemniscate or whatever. And so if you did draw these sectors in, then there's going to be some gaps on the parts of the cardioid that are a little less circular than other parts, right? And so you could just sit here all day long and you could draw in these lovely sectors. And that last one, at least according to my drawing, is pretty close to being true to the cardioid. Of course, the more you zoom in, the worse it would get. Anyhow, what we would do is we would accumulate all those sectors and we could get an approximation for the area. But as you know, where we typically head with this in calculus is we're going to eventually land on the idea that we want to find the exact area, and that's what we're going to be doing here today. So just as a reminder, the area of a sector is 1/2 times r squared times theta, where, of course, r is this radius. It's the distance from the pole out there to whatever shape it is you're drawing. And then theta would be this little central angle right there. So kind of where we ended up yesterday is we said, well, this would give us an approximation, but we do want the exact area. And I think I finished with something along the lines of, if we wanted exact area, how many of those sectors would we need? That's right. We'd need their number to approach infinity. Let's think about the implications of that, though. If we filled up even just that first quadrant with a number of sectors that just gets bigger and bigger and bigger, as that number of sectors gets bigger, what's going to happen to theta?
It's smaller and smaller and
That's
smaller.
right. We're going to pack all those sectors in there. The theta is going to get really tiny. In fact, we could say this: as the number of sectors heads towards infinity, theta would approach zero. So it would essentially be all these line segments radiating out from the center. And if we added up the area of those really skinny little sectors, we'd eventually head towards the actual true area of this, whatever this shape is, right? In this case, cardioid.
We can find the whole area of that little. We can find the whole area of that thing.
Yeah. By essentially what we're doing is, the way I would characterize it is I would say that we would be sweeping around this shape. Okay, all my drawing went away, but thankfully there wasn't that much up there. Okay. So let's do this. Okay, so the formula for this, hopefully this will make sense to you based on the idea that we're using sectors. The formula that we would eventually arrive at would be this right here, or that right there. Can you guys see this within both of those formulas? Yeah. Clearly the 1/2 is pretty obvious. The r squared, or whatever the polar equation is, squared. And then the only thing that seems a little bit different, of course, is the theta versus the d theta. So like I said, as we increase the number of sectors towards infinity, the theta is going to get tinier and tinier and tinier until it's approaching a size of 0. And that's really what d theta is. You remember maybe when you first learned about definite integrals and that little dx that's hanging on the end? Isn't the dx just like a super, super skinny width of a rectangle? So d theta would be a super duper tiny theta, super duper tiny change in the angle to create these super skinny little sectors. Okay, does that make sense? Okay. Let me put it like this. I'm going to give you maybe one more illustration before we do an example. This is so old school. Have you guys ever... Did you guys watch like the weather broadcast on the news or anything, or do you just like look at the internet?
Yeah, the weather bug. I totally
Your weather bug.
What's the weather?
Like the weather, like the weather person, the weather lady, the weather guy on
The green screen.
channel whatever. Do you guys watch that? That actually turned out okay. I did it in halves. That turned out okay. Hang on, let me finish my analogy here real quick. So in the weather forecast, they will sometimes show like a radar picture.
Oh, is that like?
And doesn't the radar picture have kind of that little moving piece to it, where there's like a kind of a, well, I would say sort of a sweeping across the map, or like sweep across, and as that little line sweeps across, then the clouds or whatever it's showing you the radar of, they change a little bit, right? Because the clouds are moving, or the rain is getting more or less intense, or whatever it is. That's kind of how I think about this. Like, we're just taking a radial line, like this one right here, taking this radial line, and we are sweeping it around the whole shape. Hopefully, no, I don't want to do that. There we go. We are sweeping it around the entire shape. And of course, the radial lines go all the way down through here, and they get really short, and they eventually are over here, and so on. And if we sweep out in skinny enough sectors, then we get a better and better approximation for the area. And if we sweep out a number approaching infinity, this is when we get the exact area. So think of it almost like that radar map, where that radar beam is really what it is, right? The radar beam is sweeping around the region, bouncing off the clouds and getting feedback and trying to show us where the rain and the snow is and all that stuff. Santi, your question from a minute ago.
I was just going to see if you could re-explain where the theta goes. Like the 1/2 r squared theta, like how theta just changes into d theta.
You take it during the
So it goes back to, let me see if I can draw a parallel for you.
Okay.
So do you remember back a long time ago, it still applies, of course, but a long time ago when we found the area of a curve in rectangular form, right? So we use these rectangles, like so. And the way we built this out is we said each one of these rectangles has a base length, right? So base, and this is a height. And we said, all right, if we want to find the area approximately, we'd say area equals base times height 1 plus base times height 2 plus ... right? We'd get as many as we need to. But then at some point in there we said, well, that's just an approximation, and it would be lovely if we could get an exact area. And so then we went to those Riemann sums, right? We said, all right, what if we did sigma essentially of b times h1 plus h2 plus ... all the way up to like hn. And then we said, hey, well, wait a minute. That only allows us to find the area approximation if there was maybe like 10,000 rectangles, right? Or, because remember, if it was I equals 1 to n, so n would be like 10,000 rectangles or 1,000,000 rectangles, or how many rectangles you wanted. You could just plug an n in there and use your calculator to do the summation, but then you'd be done, right? We said, well, what if we wanted exact area? All we had to do there was put this on the front. limit as n goes towards infinity. And then the big leap was this, once you put that limit on the front, this is the exact area, and it can be equaled by the definite integral from one end of the interval to the other of f of x times dx. And what we said was that this dx is the same as the base. Right? So the base length of the rectangle is like a super tiny change in x. So d theta is actually that super tiny change in theta. So let's just parallel this here. So for polar, we would say limit as n goes towards infinity of sigma from I equals 1 to n. So we want to have flexibility. We want to be able to have n of these sectors if we want. And we're going to force, this limit is going to force the number towards infinity. What we'd put in here is we'd say, well, the area of any one of these little sectors over here, I'll sketch these back in. These little sectors would look something like this. There, each one of those little sectors is 1/2 times r squared times theta, right? So we'd say, let me think about how I want to express this. It would be, well, here's what it would really be. It would be, I'm just going to change the order just so I can make it kind of the same. So it's going to be 1/2 times theta, and then it would be like r1 squared plus r2 squared. I'm going to get rid of these here in a second because the summation already gets us this plus that plus that. But we're just adding up all these little r squareds, right? So I'll just come back here and I'll put just r squared. And what I'm saying is just like we have this up here equaling this, I would say, all right, the integral from, and what you see up there is from alpha to beta. So alpha to beta would be angle alpha to angle beta, right? Because we're sweeping around this shape. And then our function, our f of x, like our length. So like with the rectangles, it was little tiny base times a height, right? So with polar, it's going to be a little tiny theta times a radial length, right? So we're going to say r squared is our radial length squared, if you will. And then that theta, that's what the definite integral is going to be squeezing that theta down to like a little tiny theta. So if you just wanted to put a theta there, I mean, I don't know, there might even be some places where that's what they put. But what is typically put is d theta, and all d theta is it's like expressing that it's a little sliver of a theta. The 1/2 is a constant multiple, so it could just like hang out in the front there, or it could be in there, it doesn't really matter. But the d theta, like the theta doesn't really disappear. The theta is the d theta.
Yeah.
They're really one and the same thing, it's just we're trying to express that it's a little tiny theta.
Oh, yeah, right. Sorry, for me that just connected.
Cool. Yeah, that's a great question. It's cool to make that little connection between the two, right? Hopefully that was helpful for you all.
It's also like the integral is done in terms of theta. So
Right, because r will be f of theta. That's exactly
That's
right.
what- yeah.
Yeah,
that's what I
because
thought.
so alpha and beta will both be angles.
Yeah.
They'll both be angles. So again, this is where like sometimes it's hard for people to shift from the idea of, hey, we're accumulating. Watch the hand motion. Some people, and you should be used to this because this is what we've done so far, accumulating from your perspective from left to right. Rectangle plus rectangle plus rectangle plus rectangle plus rectangle. That's not what we do with polar. We accumulate as we sweep like a radar through these sectors. It's an accumulation of area by radar sweeping as opposed to left to right accumulation. Yeah.
So because we're essentially we're not accumulating a circle, but we're going in a circle with the angles that we're using.
True.
If you switch alpha and beta, and it won't really be negative, will it? Because it's the same.
Good question.
It's the same thing.
yeah,
Essentially,
it
you're just
would,
going
because
from,
the bigger number would be on the bottom.
right, but you're accumulating from the same like kind of radial.
We can play with that.
What's wrong?
I mean, from like
We'll get a
pi to
negative
zero.
area.
I think in the first example, now, so here's something really important to realize, and this is sort of a sidelight to what you just asked. We can explore with that here in a second. since the radius is being squared, any situation like with the roses, remember how the roses had like negative radii? It's going to be squared, turning it into a positive regardless, and so that's going to be handled there as well. But let's play it with this first one. Let's mess with it and see what happens. Let's see if we go alpha to beta or beta to alpha and see if that changes. Okay, cool. All right, so I think you guys are ready to try one. Here's our first example of this. It's right here. It says, find the area of one petal of the rose given by r equals 3 cosine 3 theta.
Wait a second.
So I'm going to graph this. I think you all should graph this also. I think, doesn't this, you can use your calculator if you want. I think,
Is it? What?
Roses are
Red, violets are blue.
doesn't this one do something like this?
I just know that I'm looking.
How do you know that? Just like,
So I'm using, I know roughly what it looks like, but what I'm using is, I'm just plotting a couple points in my head, like when theta is 0, I know that cosine of 0 will be 1, times 3 is 3, so I know that one of the petals is definitely heading straight right, and I know that these roses, there's not like a perpendicular nature to them, right? The other petals aren't like perpendicular to the first one, so I know that they have to be off at kind of like that pi over, I guess it'd probably be a pi over 3 angle.
I do.
how do you know there's 3 petals?
Oh yeah, so
Feeling good.
really good.
because of this,
My petals are
the coefficient, so if it's going to be a rose like this one, the coefficient on theta,
yeah.
if it's odd, then that's how many petals are on the rose. If it's an even number, so if it was like 2 theta or 4 theta or whatever, then the number of petals is double that.
So if it was 4 theta, then it would be 8 petals. Like, what about for lemon? Like, how do you know?
That's what it was. That's okay.
Even this
For the lemon seeds, how do you know when it's a lemon seed? How do you know like how to dry it? Without just like applying.
Okay, so yeah, so did you miss one of the first days?
Yeah.
Let's not go all the way back there right now.
Look at this kid.
It's not, so honestly, it's, I know it seems like a big deal, and if you want to continue to explore it, we can do it maybe a different time, but it's not like a 2-minute conversation. The biggest thing you need to know, the biggest takeaway from all the graphs is, like if it calls it a cardioid, it would be useful that you knew what the basic shape of a cardioid is like it's got that sharp point. If it said, hey, it's one of those looped limacons, the only thing you really need to know is that the basic shape that like comes around and then there's like that extra little loop in there. If you can just like grasp that, like if it says, hey, it's a lemniscate, and you can think, oh yeah, that's that infinity looking symbol, right?
We use Math 9.
Can you use Math 9?
Do you know alpha?
Jack, I think yes. I'm gonna push you guys on this one a little bit here too. Like, and it's gonna be interesting to see what you all come up with, and how you get there. But Math 9 is fine, totally fine. So Santi, as long as you can just have like a really basic sense of, okay, cardioids look like this, lemniscates look like that, that's good. And then the biggest thing really is understanding with polar graphs for us is going to be as theta sweeps around, the radius will get longer or shorter, positive or negative. And if you can just grab a hold of that, I think you're going to be just fine. I really do. It is to a slight advantage of yours. Like if you had all the polar graphs like perfectly memorized, that would be just like a tiny bit of an advantage. But it would probably take you many, many hours to become perfect at that. And you say, many, many hours for like a sliver of an advantage? Maybe not worth it? Yeah. Let's keep working through these and maybe you'll see what I'm getting at. I always put the graphs up there just so you can visualize it better.
Yeah.
But I think as you get better, you'll need that less and less.
Okay. I mean, yeah.
Let's keep
I just
working.
wanted to know how you were able to visualize it for surface. Like that's.
Yeah. And that's how I do the roses.
Well, do we set
Yeah.
this?
Okay.
Yes, ma'am.
I was wondering if you could explain why cosine, it's like to the right and my sine, they're like an opposite.
Yeah, well, so I'm basically plotting points in my head, honestly. So I know that that 3 in the front, I know that this tells me that the max distance is 3. That's the end of the petal will be 3 away. And then what I did is I plotted a point. And I said, hey, if r is 0, or excuse me, if theta is 0, then it'd be cosine of 0, which is 1 times 3 is 3. So I know that if I'm pointing straight right, I'm 3 away, so that has to be the end of a petal.
I didn't do the first one.
And so that's, so basically, I don't know if you saw the timing of it, but basically what I did is I drew this first, and I said, okay, I know that that petal's
I
there,
haven't done it yet. I'm just.
and there's 2 more. Yeah, they're always going to be at an angle, and that's just from experience, honestly. They never go like this.
So
They never go straight up.
is cosines always gonna be like one out to the right and then two?
But then
Or,
if you do that, you have to-
If there's some negatives involved, maybe 1 to the left, and then bam.
And then sine is always gonna be one down.
Or one up.
Or one up, okay.
Yep.
I put
Yep.
them in my calculator and
No.
or what you can do is find the area of the entire road and then divide by 3.
Now you guys are starting to talk about some good stuff. I like this. So,
You have to
You
find,
could, so each petal is like pi over 6.
do you have to find what?
Half of,
could you
sorry, half
I was
of
gonna
do
do
it
that.
because essentially all you need to do is find the angles
Oh,
and
no,
just
so-
start
I
and
put it-
So,
go for one
so
petal.
a whole rose is drawn
Could you find
in
the
pi.
tangential
Wait,
So if there's
lines of like beginning
Because
of the petal?
if the number, if the
So
coefficient
that-
for
essentially
theta is
when r
odd,
equals
then it's
0.
from 0 to pi.
If it's
even,
even, it's
then
So
from
you just
0
gotta
to
find
2
two,
pi.
find those two
So
angles
since it's odd,
using
you know
dy
that
dx.
pi.
How using dy
How
dx?
many, how many
Because those are the
radians
ta-
are gonna
those are
be
the
needed
tangent
to draw a
lines.
whole rose?
You can find the tangent.
I like what you said earlier. How about just when r is 0?
You can deduce that
That does
pi
work.
over 3 radians per pi.
Okay, because I,
Right?
Let's explore a little bit.
That makes sense?
Divide by 2 is pi over 6 is half.
So pi over 6 is half a petal.
Let's
Negative 1.
let me hear some ideas from you guys. Like, just these can just be kind of conceptual ideas. Like, I thought we could do this and then that, or whatever. What do you think? What big conceptual approaches did it occur to you?
You can find the bounds of one petal, so from 0 to 0.
From
So
0.
r equals 0 to 1, r equals 0.
Okay, so this is a good strategy. Let's run this through and see what happens. So the basis for this, of course, is that each of the petals start and stop at the pole. And when the curve is at the pole, r is 0. So 0 equals 3 cosine 3 theta. And of course, that means 0 equals cosine 3 theta. This is where our unit circle skills get to come to the forefront. Oh, yeah. Inverse cosine of 0? What are the angles we're talking about? Pi over 2. And there's lots of them, right? There's pi over 2, 3 pi over 2, and you used to said every odd pi over 2.
Oh, you could say we need 5 over 2.
Well, we could do all these, right? 5 pi over 2, 7 pi over 2, ... equals 3 theta. There's a bunch of them. So then I would then divide by 3, and I'd get pi over 6, pi over 2, 5 pi over 6, 7 pi over 6, so on and so forth. Of course, that pi over 2 looks like a little bit of an oddball, but it's really 3 pi over 6. So it's 1,357 pi over 6. Okay, and that's equal to theta. So those would be all the angles, or not all of them, those would be a selected listing of the angles in which r is 0, right? Okay, so then how would you use those to set up a definite integral that will allow you to find this? I'll fill it out here. Isn't it going to be 1/2 integral from alpha to beta, we haven't figured that out yet, of 3 cosine of 3 theta quantity squared? D theta? And we know that it's got to be that, but we just got to figure out the alpha and the beta. So what do you all think based on what we just did?
I'm going to go from pi over 6 to pi over 2.
Pi over 6 to pi over 2? Okay, what do you think about that?
I went 0 to pi over 6
That is a
times.
petal.
So I'm going to draw in a radial line, and we'll just discuss this, okay? So pi over 6,
If you put your window from pi over 6 to pi over 2, it's that petal.
pi over 6, am I correct? Pi over 6 is right there?
yeah.
So pi over 2 is pointing straight up.
Same thing.
And this is, now listen, this is where this seems a little strange because
Oh, 'cause you
there appears to be no petal there.
However,
However, what?
The pi over 2 equals 0, which we know.
you have to.
Where is the petal?
It's in the third quadrant, like I've been telling you all.
Isn't it right there?
Haha.
So when all of these radial lines, if we plotted these points, all these radial lines are pointing this way throughout here, right? They're all pointing towards the first quadrant. They're going this way, pointing that way, so on and so forth. But for that entire range of thetas, I believe you should get negative r's each time.
And the negative r would equal, like,
And negative r would be putting it down there in the third quadrant instead of in the first quadrant. Let me ask you this.
Like,
Um,
you're using the angles from here.
so let's test this out. Like, so we have this supposition, hey, maybe, just maybe, all of those angles are producing that pedal in the third quadrant. Let's try some other stuff out. Here is, well, did anybody think of it differently? Let me just put it that way. What'd you do, Nick?
Well, Jack helped me like actually get it on paper, but like my idea was that if you take half of a pedal,
Yeah?
you can multiply it by 2.
Yeah.
And then you get a full pedal.
Okay, so let's do that.
So I looked at the first pedal that's going to the right.
Yep.
And noticed that it's starting from 0. So if that's your beta, alpha.
Okay, so there's my purple radial line. Oops. So you're saying we start there at 0 and we go into the first quadrant?
I went to pi over 6. And then I multiplied it, and then I multiplied that by 2.
Okay, so let's try this out. I think I get it. So it'd be 1/2 integral from 0 to pi over 6. Okay, 0 to pi over 6 of 3 cosine of 3 theta, quantity squared d theta. But then that's exactly half of a pedal, like you said.
So we take,
So they just go 2 times that.
yeah, so you just, yeah.
Okay.
that's why I was.
Does that seem logical to you guys?
That's what I was like, 'cause I just thought
That's
since
what I
the
was
pedals
thinking.
were
I thought
symmetrical, you could just find that the first angle and then just do the negative of the other angle for the other bound.
Okay, so let's
It's the same.
Yeah.
let's think about that.
If you do pi over 6 to pi over 6.
So this would be, 1/2 integral from negative pi over 6 to pi over 6, right? That would be going from, I'm going to keep with my color coding if I can. Wouldn't that be going from this radial line to this radial line? And so it would be all of this from here up through that purple. That would give me, theoretically, I think, one full pedal. So then it would just, of course, again, be the same r squared, d theta in there. Make sense? Yeah, Peyton.
What I did is I went from 0 to pi and then divided by 0.
Okay, so this is another way to do it.
Still, actually, I love that.
Couldn't you say, now this does require, if you want to be quick about it, it requires a little bit more knowledge from the perspective of an odd pedaled rows only needs 0 to pi to complete the full rows, right? But if you know that, then you could just say 1/2 integral from 0 to pi of r squared d theta. That would give me the full rows, right? The area of all 3 pedals. So then what would I do? Divide that by 3,
That might be the easiest way to go.
and I would get there too.
Yeah.
That makes sense?
Because then you don't have to find the angles.
You just,
Sure.
You have to use your knowledge of the.
Yeah.
And so, yeah, if you know a little bit about how the rows is formed, then that would be a way to do it too.
Then for sine,
Bang it out.
0 to 2 pi, right?
So say it one more time.
For sine.
No. If the coefficient on theta, so in this case it's 3 theta, if that coefficient was an even number, like 2, 4, 6, 8, then you have to have the full 0 to 2 pi. It's about the evenness or oddness of that.
Okay, I thought it was about sine or cosine.
Nope. If this was sine of 3 theta, it would be the exact same shape. It would just be, well, let's see here. It would just be rotated. It'd just be rotated 90 degrees, essentially.
Okay, so,
Pi over 2
okay,
radians.
I thought, so that's the same with the window, right? When you're doing the window on the graph?
You mean the theta window?
Yeah, when you're tracing it.
Exactly, yeah. 0 to pi will give you the whole rows here. But if it's an even coefficient, you'd need 0 to 2 pi to get the full trace.
I gotcha.
Yep. Good question. There was somebody else that the thought?
I had one, but I think I just answered it.
Okay, figured out. Hey, so here's something cool to think about, you guys. Now, I don't know, have you guys all confirmed this, that all of these, all 4 of these, are the exact same numerical answer?
Yep.
They should be. It all seems logical, like all of your approaches were well thought out. I think it's really good. So here is maybe a natural question of this, like let's say that you were going to be assessing this. Hey, does everybody know how to find this? you understand for me, I could give 10 quizzes, one each to each of you, and I could potentially get 10 very different looking answers, right? So number one, I'm totally okay with that. So I'll figure it out eventually, even if you do it complicated or whatever, I'll get it figured out. The other thing to think about here that's really important is that these can be presented in a multiple choice format. So this is where your ability to think flexibly instead of rigidly is very good. Because if you looked at these four, and there obviously we could have done more options than even just these four, right? There would have been other ways we could have written out this. If you, there are an infinite number of ways. You're correct. But even if you take the whole, hey, we could spin around the circle a zillion times or whatever. Even if you take that out, there's still a lot of ways. Even if you just restricted yourself to just the 0 to pi, we could think of other ways to do this that would be logical. Might be a little complicated, but we could still do it. Say again.
Let's find half of a pedal and then multiply it by 6.
That just becomes an arithmetic gymnastics, right? Here's my point. I want you to not, right now today, adopt, this is how I'll always do it. I want you to try to see the concept of what's happening and have the flexibility in your thought to say, wow, here's how I normally do it. And I just looked at these 4 answer options on the multiple choice, and none of them agree with what I just did. I want you to work on that flexibility of saying, well, I'm really confident my answer is right. How can I get this in the same form as what will eventually be the correct answer option? Make sense?
So we could have done the integral of 5 pi over 6, 7 pi over 6.
Yeah.
Just
That's
given
what I
that
did.
label.
Don't worry.
You absolutely could have done that. Yeah, so there's another very logical way that's not weird, convoluted. Let's spin around the circle a million times, right?
But
Totally
that's-
logical.
Okay,
Say again?
so this could be a question on the AP exam, and it would be just, could it be from 5 pi over 6 to 7 pi over
It could.
6? Or from pi over
I will say that I will never do this. I know the College Board will never do this. We're never going to, on purpose, try to make it more complicated than it needs to be. For instance, I'm not going to say, hey, let's find 1/16 of the petals area and have these really odd, strange angles and then just multiply the whole thing by 16, or something like that. It's never going to be that. It's going to be, hey, let's go from negative pi over 6 to pi over 6, or let's find the area of the whole thing, but then the answer is basically just 1 petal times 3. That makes sense? So, yeah, it really, honestly, the thing that I always get in trouble with, let me put it to you like this. Maybe this will be reassuring. The thing that I always get in trouble with on the whole item writing team is, they'll give me feedback and they'll say, hey, neat question and everything, but we need to make this more accessible, less complicated. That makes sense? So I'll send them a question, say, hey, I think this would be a good question. They're going to say, good question, but what if we did this? It would make it a little simpler for the students to get to the concept. So when you think about the AP test, when you think about my test, that's the spirit of how can we be for sure that you know what you're doing without making you spin around the circle 30 times or do some weird angles or some other artificially complicated thing. It really is the case. It really is. I get in trouble all the time, not in bad trouble, but they're like, come on, simplify. Everybody does. So anyways, yeah, go ahead.
Promise last question. Do you think it would most likely be one of these 4 options on
Oh, man.
Because these are the 4.
Yeah, let's see here. I mean,
Wait,
Could you have done
I'm thinking,
different angles?
I'm thinking that I don't think it would be the orange one, and here's why. The orange one has kind of a little bit of a stipulation that you know a little bit more about polar graphs than maybe some other folks,
Yeah.
and that could be the differentiator between success and failure. So I don't think it'd be the orange one. I think it would probably either be the green one or maybe the purple one. I would guess that would probably be the correct answer option. The green or purple would be my guess, but. Oh, the black one is clearly correct, but I bet they wouldn't select the black one because of the whole there's no rows there.
Yeah.
I'm confused. Oh, it's down there. They would probably see that as maybe a little too confusing. Yeah.
So doing the 0 to pi one, but working backwards. So let's say you set 3 cosine 3 theta equal to 3, and that way you find when the radius equals 3.
Sure.
You end up getting 0 and pi over 3 instead of pi, because you don't How does that work?
Yeah, good question. Okay, so what he's saying is if you go 3 equals 3 cosine 3 theta, which would tell you the angles at which you're at the very end of the pedal, right? So, and you said this gives me theta equals 0 and pi over 3, like if you just limit it to those? Okay, good question. So I'm going to try to do this in yellow, so this will show up. So 0 is here. So if you did integral from 0 to pi over 3, right? Here's what would happen. You would accumulate little sector areas all the way up through here to pi over 6, right? And once you're pointed at pi over 6, you're going to be right there at the pole. Then once you go from pi over 6 to pi over 3, this is where we start the negative radii. And so the first one would be here, and then here, and then here, and then you'd actually stop right there.
But you'll get the same amount.
Because you'd get half of one of them and then the half of another one. That would still work.
Oh my god.
Literally
That's-
do
That's so annoying.
any accumulation along the rows where the
Come on.
change in theta is pi over 3.
That's correct.
Oh,
Oh, that's dang.
That's correct.
that's so annoying.
That doesn't feel right.
And so that's why I say we're not going to say, ooh, let's go
So if it's a
pi over 31 minus pi over 3, for the two, we're not going there, right? We're going to keep it as like straightforward as like anybody could argue. Like that's still pretty straightforward. That's where we're going.
that works because it's a 3-petal rose, right? Like if it was 5 petals, would it have to be pi over 5? Because
I'm
that's
writing
so
that down.
annoying.
That is a lot.
There you go.
So the goal that you guys have done, let me say this. You guys have done an outstanding job of discussing and discovering and figuring things out. The goal of this is not for you to say, oh, I like that way. I'm going to marry that way because that's the best way. The goal is that you understand what's happening and how you can work within all of the things that are happening to get to where you want to go. That makes sense? Like master it. Don't memorize a formula. Like seek to master it. Yeah,
So if it were an even number, like let's say 3 cosine 2 theta,
right.
would it be 2 pi over 4?
Would it be...
Like would the
Well, so now we're talking about...
pi,
Yeah. So now we're talking about we need the full 2 pi.
yeah.
And if it was like a 4-petaled rose, then yes, it'd be a pi over 2. Like a difference of pi over 2 should get you one full petal.
Okay, so basically, if you want to do it that way, you just take like the entire thing divided by number.
When you know.
Just like we did here. Just like you said.
So if we always do pi over the number of
I didn't
petals,
understand what it
it'll
was
be
doing
fine.
until I just read
Number
it.
Yeah,
of
the-
petals.
Pi over the number of petals are pi.
Or 2 pi. 2 pi if n is even.
See, now this is just too complicated.
So this is where you want to be careful, right? Hey, listen up. I say this all the time to my Algebra 1 students because my Algebra 1 students, they always want little tricks. And what I say to them is, if you have a series of tricks and all the tricks sort of sound the same, and it's hard to like differentiate between the tricks, I think you're the one that's tricked because now you're having to keep track of all these tricks, and now you're confused by all the little tricks. So just be careful. Just be careful.
If that's what makes sense in my brain.
But then what if the question writer wasn't thinking that way? And also you're like, you didn't think my way. I can't answer this.
Well, on a free response, I could do it that way.
Yes, you could.
Great.
Absolutely you could. But I guarantee you'll at least see at least one of these on some multiple choice scenario. Guarantee it.
You need to know all the ways.
Guarantee it. Yeah, for sure. Hey, guys, believe it or not, we just spent our entire class on one question, but I think it was totally worth it because I think tomorrow now, when we run through like 2 or 3 of them, you're going to be like, okay, I get it, because you guys have put a lot of effort on trying to understand what's happening. And I had fun talking to you and listening to you, so it was good. So, have a great rest of your day.